Okay, so hopefully you're somewhat comfortable or used to Laplace transforms. So now we're gonna go backwards, right? We're gonna reverse the process and find the inverse Laplace transform now. Okay, so this is just a review of the Laplace transform. It takes a function, say f of t, and converts it into another function, capital F of s, right? So again, they don't even live in the same space, right? So the idea of the Laplace transform is you take this function and put it in, but go backwards now, right? So instead of going backwards like this, let me just create a whole new machine here, and I'm going to call this L inverse for the inverse Laplace transform, right? And yep, so it's going to take as its input a function of s. Let's say capital F of s. That goes into the function, and what comes out is your little f, right, of t. Okay, so this is the inverse Laplace transform. Okay. So yeah, since we already know the Laplace transform of quite a few functions, let me just remind you what they were. The Laplace transform of 1, of course, was just 1 over s. So now, in terms of the inverse Laplace transform, if we take the inverse Laplace transform, or just L inverse, of 1 over s, we just get 1, right? So remember, the Laplace transform of t was 1 over s squared. So now the inverse Laplace transform of 1 over s squared is just t. And maybe we should do this more generally. Instead of doing t squared and t cubed and so on, we got that the Laplace transform of t to the n, remember, was n factorial over s to the n plus 1. So writing it as the inverse, we get the inverse Laplace transform of, let me try that again, of n factorial over s to the n plus 1. That has to be t to the n. Now, you can play around with this. If you just want to do, say, s to the n, then you would do that and then do t to the n minus 1. But I'm gonna just, just going back and forth like this, I'm going to leave it in this form here, if that's okay. Yeah, what else did we do? The Laplace transform of e to the at, where a was just a constant, was 1 over s minus a, right? So that means the inverse transform of 1 over s minus a will just equal e to the at. And you can see, by the way, this works. If a is 0, by the way, e to the 0 is 1. So this is just 1 over s, right? You just get back to this again. So yeah, some of these are a little bit redundant in the sense that this one's a little more general than this one up here, right? But yeah, that's fine. What else do we do? Oh, sines and cosines, right? So the Laplace transform of sine of kt, this is the one we worked out using the definition, and we got k over s squared plus k squared, right? So the inverse Laplace transform of k over s squared plus k squared has to be sine of kt, right? And so on. There's a whole bunch more. Maybe just to do the cosine one, and then we'll leave it at that. But there's a whole bunch of them, in 7.2. This is s over s squared plus k squared. And so the inverse Laplace transform of s over s squared plus k squared, will just be cosine of, sorry, I didn't mean to make that negative. Let me try that again. Yeah, cosine of kt, right? Okay, so Right, so again, this is just knowing what the Laplace transforms are, then you know the inverse Laplace transforms, you just work backwards, okay? And like the Laplace transform, the inverse Laplace transform, inverse, is also linear. Okay, so remember what that means. If I take the inverse Laplace transform of, let's say, alpha times capital F of S plus beta times capital G of S, then you're just going to get A times little f of t plus beta times little g of t, right? So, so this allows us to calculate inverse Laplace transforms more easily, right? Because remember, there's no definition here like there was with the Laplace transform, right? I mean, if you think about it, the Laplace transform was some sort of an integral. So you might think, well, then the inverse Laplace transform is some sort of a derivative. And that may be the case, but I don't know what it is. I don't know if there even exists a formula for it. Yeah, it can't be an easy one. So no, so we really can't compute inverse Laplace transforms by definition. We simply have to look at the corresponding Laplace transform, the forward Laplace transform, and just kind of work backwards from that. So that's kind of the best we can do here. But still, that allows us to calculate a whole bunch of Laplace transforms. So let's just do an example. How about the inverse Laplace transform of, how about 2s minus 5 over s squared plus 9. Okay. Right, so again, there's no integral here. We're doing the inverse Laplace transform. But remember, it's linear, so we can split this up. We can treat this as 2 times the inverse Laplace transform of s over s squared plus 9, right, minus 5, right, that's a 5, not an s. This looks kind of like an S here, doesn't it? Oh, wrong color. Yeah, so this was supposed to be a 5. All right, it's a little better. So minus 5 times the inverse Laplace transform of 1 over s squared plus 9. Okay. So s over s squared plus 9, that's this right here, right? So that's just cosine of kt, k being not 9, but, right, that's k squared is 9. So if k squared is 9, k is 3. So this is just going to be cosine of 3t. Parentheses are optional, right? Minus 5 times 1 over s squared plus 9. Now that's way up here, but remember, k is going to be the same here. K is going to be 3, but we don't have 3 in the numerator. We only have a 1. Right? So remember what to do here. Just multiply by 1/3 on the outside, and then multiply by 3 on the inside. Right? Just like you're doing an integration by substitution, right? Very similar. So now, this whole thing here, right, should be sine of 3t. But now we have this minus 5/3 in front, right? So putting it all together, you get 2 cosine of 3t minus 5 over 3 sine of 3t. Right? And that's the inverse Laplace transform of 2s minus 5 over s squared plus 9. Okay? So, yep, that's the idea, right? Same thing with just, let's do the inverse Laplace transform of, how about just 1 over s to the 4? Well, if you remember, way up here, there's the formula for the Laplace transform of t to the n. So the corresponding one would be this one up here. And since I messed it up, let me just write it down again. Like I say, this is one you can look up pretty easily. So we have n factorial over s to the n plus 1. And that's just going to be t to the n. So if n plus 1 is equal to 4, here our n is actually 3. Right? And yeah, the problem is this is 3 factorial in the numerator. We don't have that. We only have the 1. So that's, because it's just a number, that's not a problem. Just multiply by 3 factorial. I'll write it as 3 plus 1 if that helps. As long as you also divide by the 3 factorial, right? Which is just 6, right? 3 times 2 is 6. So this is 1/6 times t to the power 3, right? Or if you prefer, t cubed over 6. Not picky, either way is fine, right? So, yeah, so that's the idea. Right, so you just have to use the fact that the inverse transform, just like the forward transform, is linear. Okay. Yeah, let's do a slightly more difficult one. And well, I'm going to say slightly more difficult, but let's see. Yeah. All right, let me just put it up so I'm not wasting time here. Okay, so yeah, so we want to evaluate the inverse Laplace transform of 8s squared minus 6s plus 20 all over s cubed minus 2s squared plus 4s minus 8. And that looks pretty crazy, right? I mean, we did one sort of similar to that here, but this one, yeah, this one's not going to be quite as nice. So the first thing you might want to note here is that in the denominator, you really have s squared. Oh, yeah, you take out the s squared and you get s minus 2. And here you take out the 4 and you get s minus 2. So the denominator factors as inverse Laplace transform as s squared plus 4 times s minus 2. Okay, and that's going to be very helpful to us. So we know we're going to take the inverse Laplace transform, right? I didn't have to write it down again. So we have 8s squared minus 6s plus 20, right, all over s squared plus 4 times s minus 2. So I think some of you see where this is going, right? You notice I didn't try to factor the numerator. I mean, you can, but it's not worth it. So what we're going to do here is decompose this, right, into partial fractions. So remember how that works. We get as plus b over s squared plus 4 because it's quadratic, right? We need a linear term in the numerator. And then some constant c over s minus 2. Right? So this is partial fraction decomposition. Right. Okay. So, yeah, you did this in Calc 2. You did this in pre-calc. Let's do it again. So usually what you do is you multiply both sides by this denominator, right? And that just gives you the numerator on the left, plus 20, right? And then on the right, you get as plus b times s minus 2, and then c plus c times s squared plus 4. Right. And, you know, the long way is to expand all this out and collect like terms in terms of s, and then get a system of equations that you solve, right? But, you know, I like the shortcut here. Obviously, if s is 2, then what do we get? We get 8 times 4 is 32 minus 12 plus 20. So 32 minus 12 is 20. 20 plus 20 is 40. I hope that's right. And on the right, this is 0, right? 2 minus 2 is 0. So you just get c So this is going to equal c times 2 squared is 4, 4 plus 4 is 8. Right? And so that just tells you that c is equal to 5. Right? So we'll plug that in here later. Right? And now just pick some other number for s. 0 works pretty well. So if s is 0, then the left side is just 20. And the right side is, well, 0 plus b times negative 2. So you get negative 2b plus c, which remember is 5, times 0 plus 4 is 4. Right? So, oh, I think we get 20 on both sides. So negative 2b equals 0, which means b is just 0. Right? And then we need to find a, right? So pick some other number for s. How about just 1? So we get 8 minus 6 is 2. 2 plus 20 is 22. And then we're going to get a plus b, but remember b is 0. And then 1 minus 2 is negative 1. And then c is 5 again. And then 1 plus 4 is 5. So 5 times 5 is 25. So what do we get here? Well, I think we get 22 minus 25 is negative 3 equals negative a. Yep, so a is 3. Okay, so, yep, so that decomposes this into its partial fractions. I guess we get 3 times s plus 0, so 3s over s squared plus 4, and then plus 5, right, not s, that's a 5. Does look like s. So 5 over s minus 2. Okay. Now, we're not done. Remember, this is what we're trying to find the inverse Laplace transform for. Right? So all we did was we took this thing here and we just split it up into its partial fractions. So we still have to evaluate the inverse Laplace transform of, I forgot, 3s. Right. That's an s over s squared plus 4 plus 5 over s minus 2. And again, we do something very similar we did here, right? We split this up by linearity. So splitting it up, we get 3 times the inverse Laplace transform of s over s squared plus 4. Hopefully you remember what that is. I think that's cosine, right? And then plus 5 times the inverse Laplace transform of 1 over s squared plus 4. And that's going to be the sine, although remember, for the sine, the numerator can't be 1, it has to be k. So what's k here? K squared is 4, so k is 2. So we need the numerator here to be 2, and that's okay as long as you also divide by 2. Okay, now we just use the definitions up here for sine and cosine, right? Here they are again. Okay, yeah, I know I should know these by now, right? So 3 times the cosine of kt, so k is 2, so 2 times t again, plus 5 over 2 times sine of 2t. Okay, so there you go. That's going to be the inverse Laplace transform of, well, all this up here. So, yeah, unfortunately, in many cases, you're going to have to use this partial fraction decomposition. It's typically the way to go to be able to decompose this using linearity, right? Because one thing I can tell you for sure, right, and this works forward and backward, right? If you take the Laplace transform of a product, right, you do not get the product of the transforms. You don't get f times g, unfortunately. So likewise for the inverse Laplace transforms, if you have a product, right, let's say that's g here, right? Yep, you don't get f of t times g of t. Right. So Yeah, so you're not going to be able to do things like the inverse Laplace transform of, say, S times, I'm trying to think of something. Well, yeah, we could do S times 3 over S squared plus 4, right, which is the first term here. But yeah, you cannot split it up by the S and then the 3 over S squared plus 4. It just doesn't work. Okay, so yeah, products are not well behaved like this. For products, these just don't work. There are ways, it's not really a product here, but there is a way to do something like this. If you think about sort of like a reverse product rule, so there is no product rule for either the Laplace transform or the reverse Laplace transform. However, there is something called convolution, but we're not going to get into that. I think that's all the way in section 7.4. So if you're curious about it, go right ahead and look it up, but we're not going to deal with that, right? And we're not going to need it. We're not going to need things like this. If we see a product, then it's probably going to be something more direct. In other words, something involving one of these formulas up here. Okay, so as long as you know these, or at least be able to look them up, then this should not be a problem here. I realized I messed something up here. Okay, my bad. I can fix it. All I did here is this 5 over, yeah, it's the second term. Right? Look at the denominator. It's S minus 2, not S squared plus 4. So I can just magically erase this and put in the S minus 2 here. So that was originally S minus 2, yep, right, not S squared plus 4. And because of that, we didn't need the 2 in the numerator here anymore. We can just get rid of that. Hang on, let me erase everything. Okay, I think this is right then, right? So, yep, you can take out the 5 here. 5 over S minus 2. But yeah, the Laplace transform of 1 over S minus 2 has nothing to do with sign. It's, well, come back up here, 1 over S minus A. So A is 2. You just get e to the 2A. E to the 2t. Okay, so way down here, yep, this is just going to be 5 times e to the 2t. Okay, that's the answer. Sorry about that. Yep. I was a little lazy here, and I put this denominator as S squared plus 4 also. It's not. It's just S minus 2. Yeah. And I had it right here too. I don't know what happened. So sorry about that. But anyways, that's fixed, and this is the final answer here. So yeah, here's the original problem, which I messed up already. The 8s squared minus 6s plus 20 over s cubed minus 2s squared plus 4s minus 8. So the inverse Laplace transform of that is this down here. Right? Okay. Yeah, I think I'm going to do one more thing here. Oh, and I'm running out of space, so I'm going to erase all this and then start over with kind of a new concept here involving the inverse Laplace transform, but we're going to take the forward Laplace transform of derivatives. So, okay, so that should clear everything. And now we're going to take transforms of the derivatives. So Laplace transform of derivatives. Okay. So for example, let's take the Laplace transform of, instead of f of t, how about f prime of t? Well, this is just using the definition. Right? It's the integral from 0 to infinity of e to the negative s times t, but times f prime of t dt. And again, I'm not giving you what f prime is. It's just some function. But let's see what happens, right? If we apply, well, I think we have to apply the, not substitution. What is this called? Oh, by parts, integration by parts, right? So let's just integrate by parts here. So this is already the derivative, right? So that means v is just f, and du is negative s times e to the negative st. So applying integration by parts, we get u times v, so that's going to be e to the negative st times f of t, evaluated between 0 and infinity, minus the integral of v du, so minus a negative is plus s times e to the negative st times f of t dt. So, yep, this is s times t. I know that looks like a minus. S times t here. So, obviously, if t is infinity, this is 0. And if t is 0, then this is going to be e to the 0, which is 1, times f of 0, which we don't know what that is, but it's just some function evaluated at 0, plus s times, this is from 0 to infinity. Well, this should look familiar. This integral here is nothing more than the Laplace transform of f of t, also known as capital F of s. So there you go. This is s times capital F of s. So that's the Laplace transform of the derivative of f. Okay. And we can repeat this process if you, right, take the Laplace transform of the second derivative. Well, you can imagine you're going to have to use this integration by parts twice. And here's what you get. You get s squared times f of s minus s times little f evaluated at 0 minus f prime of 0. And now I realize my mistake. There's another mistake here. So remember, this is 0 minus f of 0 up here. So there's a minus sign in front of the f of 0. And so because of that, maybe I'll just write it all over again. So the Laplace transform of the derivative of f is going to be s times f of s minus little f of 0. Okay. Yep. And you can keep going. In fact, maybe I'll write down one more, even though you're not going to see it. You might see one in the homework where there's a third derivative, but not likely. So it's s cubed times capital F of s, right, minus s squared times little f of 0 minus s of f prime of 0 minus f double prime of 0. I think that's it. I think that's what you get if you do this a third time. So in general, your Laplace transform of the nth derivative of your function is going to be s to the n times the Laplace transform of f, right, minus s to the n minus 1, right, of, yep, f of 0, little f of 0, right, and then minus s to the n minus 2, first derivative of f evaluated at 0, and so on, right? You just keep subtracting, dot, 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 and then minus, let's see, this is going to be not the nth derivative, but the n minus first derivative evaluated at 0. So, same pattern, right? The pattern just continues like that. Obviously, this is not one you really need to know. For our purposes, the first and second derivatives, these are the ones that are going to come up quite often. So these you should know. These you really should know because they're going to come in really handy very quickly. Okay, you know what? I think this is okay, so this is what we're going to need. And I think I'm going to stop right here we're not done with this section. Okay, so before we end, you might ask the very obvious question. We've been dealing with Laplace transforms and inverse Laplace transforms, and so you might ask, where's the differential equations? Right? What's this got to do with differential equations? Right? Because that's what we're, right? This is the name of the course, right? We're trying to solve differential equations here, and we've been dealing with these Laplace transforms, which seems like completely unrelated. Like, what does all this mean? What are we doing with all these Laplace transforms? And yeah, so obviously I'm not just doing them as, for my health. I'm not doing them because it's a neat little device that I like to, just think about in for its own sake. They come in very handy in solving differential equations, right? So we'll do that in the next video. So part 2 of this section, where we actually use this to solve differential equations. How's that? All right, so that's coming up.